Welcome back to Physics Clinic at the Red Rose Academy. In continuation with the last topic, this is actually the first order reaction. We are now seeing the first order reaction. Let me explain you fully. So this is what we saw. The final equation, it shows like, okay, this is the final equation. Or we can represent like this also. Okay, like this also we can represent. In this, if you put T is equal to T1, then the concentration of R will be R1, right? But this won't be changing. This is initial part, initial concentration, it won't be changing. If you put T is equal to T2 and R is equal to R2, like that, where these two are the two concentrations, you can able to find out the difference between these two. Like the average, what we did, average rate, right? So ln of R1 minus ln of R2 is equal to KT1 minus of minus KT2. So take K outside, so T2 minus T1. So the T2 becomes plus now, minus of minus will become plus. So K can be written like this for the two different time period. That is a kind of average, okay, average time. And equation 4.9 can also be written like this, we know. And this can be taken anti-log. See, what is an anti-log? You must know the logarithm, natural logarithm and the log to the base 10. Okay, common logarithm. It is logarithmic base 10. Okay, this is log. Natural log always represented as ln. So ln is log to the base e. Okay, this is log to the base 10. So these two are different. We can able to derive ln to log by multiplying 2.303. If we multiplying 2.303 into log, that will be ln. Okay. Okay. So, and antilog is something different. Okay. I'll do another video for you kids, definitely. Then, so ln R by R naught is equal to minus KT is here. And if you take if you want to take an antilog means if you take exponential on both sides, then log will cancel. So, you have studied about the functions in sets, relations, and functions, and also in limits, right? Limits and derivation. So differentiation, that also you have learned, right? So a lot of logarithmic functions and exponential functions. Logarithmic and exponential functions are inverse together. So if you take exponential on both sides, take exponential on both sides, then it will be like e power ln of concentration R by concentration R naught. That is equal to e power minus kt, right? So e and ln gets cancelled, I told you now. Then what is the resultant? R concentration by R naught concentration is equal to e power minus kt. Bring this R naught here, so it leads to this equation. So it is also look alike that y is equal to mx plus c. If you compare this, then we can able to plot the graph against R and T here. T is in the exponential part. Okay, exponential of minus kt, right? R is here. Then how can you write now? Slope is minus k as usual. Okay, you can able to find out this also. Then what is the first order equation? 4.10. Okay, this is the first order equation. There also you can convert ln to log. I told you, no? If you multiply 2.303 into log, that will be ln. Okay, here it is given. Then, okay, if we plot a graph between log of R naught by R versus T, then the slope will be like this. Okay, so this is like a Y. This is, okay, sorry, this is like a Y, and y is equal to mx. Here no c, that is no y intercept. So this is a kind of y. And k by 2.303 is slope, and t is x. Like, okay? So y versus x, and this is the slope. Here example is given. What is an example? The graph is following back. The example is given here. C to H4, and H2 it gives what? C to H6. Okay. This is the example for, that is the hydrogenation of ethene. C to H4 is ethene. After hydrogenation, it becomes ethane. Okay. Hmm? So ethene added with hydrogen, it gives ethane. So what is the rate? Rate is equal to K into C2, concentration of C2H4. Okay. So why we are taking this as first order? This is also very important, Ra. You have to keep in your mind. You must know which comes under the first order, which comes under zero order. So many examples are given for, okay, first order, zero order, and everything. Okay. So you have to go through all these things. Very important to you. Okay. We'll see the example of uh, the first order reaction. So what all comes under the first order reaction? All natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. So this and all we are going to see. First of all, we saw hydrogenation of ethane. Here they wrote rate as K into C2, concentration of C2H4. But there are two molecules here. Okay, two reactants. Hydrogen also there. But hydrogen is not included in the rate equation of the first order. Right? Why? Why hydrogen is excluded in this? Students, you can write the point. Okay, why hydrogen is excluded in this? Okay, so hydrogen gases, can you write? Hydrogen gas is present in excess, large excess, or it is tightly bound to the bound on the metal catalyst surface. So metal we are using uh, to uh, to perform the reaction is metal. This metal is a catalyst metal. It won't react with the reaction. Okay, but this hydrogen is tightly bound with the metal catalyst. Okay, so it makes the reaction depends only on the mm, amen concentration of ethene. Okay, that is, we can say, catalyst saturation it is. Okay, so in the presence of nickel only here. Okay, this is the metal surface. Nickel is the metal surface. We can nickel, palladium, platinum, etc. It is fully covered with absorbed hydrogen atoms inside the metal. It is absorbed hydrogen atoms. Okay, so that suppose if you change the pressure, concentration of the hydrogen gas, it does not alter the number of active species, okay, on the surface. So this is the main reason. Okay, wow. Hmm? Okay, so for the first order behavior, the overall speed relies entirely on how much ethene approaches and reacts on the surface. Okay, okay. So take down this and we'll see the graph. So we already saw what is the slope and everything. If you see this graph like ln of the reactant, if it is given, okay, ln of the concentration of the reactant with the time, then the slope will be negative. Okay, ln of R naught is the y-intercept. If you take the slope like this, log of R naught by R with time, then the slope will be positive. This is the major difference. K by 2.303, it is the positive slope. So the straight line is like, there is no y-intercept. So it starts from origin. Clear? So these two example you have to take down. This one, okay? This is the reaction. You know how it comes, okay? And another one is this reaction. This one. You can take this one also. Equation 4.9 and equation 4.15. Okay. This is 4.15. This, sorry, it is 4.9. It is 4.15. Okay. And see, we saw, right? So the radioactive isotopes, okay, radioactive decay, artificial decay of unstable nuclei also under first order kinetics. So take a note of this, keep in your mind. Radium, it provides helium. Okay. Actually, maximum artificial radioactive decay only it is given. Okay, so not everything, only the artificial radioactive decay. Here, for example, if you are having radium's atomic number and mass number, what is radium's atomic number and mass number? Hmm? So what is the number given? 226, right? 226, and the sorry, mass number is 226 and the atomic number is 88. Clear? So it is radium. And here it gives helium. So you have to reduce the mass number as minus 4. So 226 minus 4 is 222 and 88 minus 2 is 86. Now it comes radon. Radon is having the mass number 222 and the atomic number 86. Is it clear for you? Okay, so decomposition of N2O5 and N2O are some more examples of first order reaction. So you know that, right? Decomposition of N2O5. So we saw in that structure, right? Actually, N2O5 and N2O, dinitrogen pentoxide and nitrogen dioxide. Okay, so the example is given here. So these are all the first order reaction. Okay, examples are very easy. You can take down this. Then first order gas phase reaction. So A gas plus B gas plus A gas gives decomposition reaction. Mostly the first order reaction we saw is mainly decomposition reaction. In the decomposition reaction, A of gas, it gives B of gas plus C of gas, right? So let Pi be the initial pressure of A and Pi only, no, PT, Pi, right. And PT, the total pressure of the time, totally, at time T. And the integrated rate equation for such a reaction can be derived as total pressure is taken like this. Okay. And these are all the partial pressures of A, B, C respectively. Then X atmospheric pressure be the decrease in pressure of A at time T. And 1 mole each of B and C is being formed. Okay. See, A is decomposed to form B and C right now. So X atmospheric pressure is now decreasing in pressure of A. So due to the decrease of pressure, so if the pressure is decreased, then what will happen? Okay, it will, I mean, 1 mole is now 1 mole of B and C is formed. It is a product is formed now. So the increase in pressure of B and C will also be X atmospheric pressure. Now here the decrease in X atmospheric pressure moves to the product. Okay, so what is at time T is equal to 0? The initial pressure will be, now the pressure is reduced to X. So Pi minus X is the remaining pressure. Initially, the product is 0 atmospheric pressure. Now it has X atmospheric pressure. Okay. Then you have to add the total pressure of A, B, and C. So it will be Pi plus X. 1X gets cancelled. So what is this? X is equal to Pt minus Pi, right? From this we can able to write. So what is PA? PI is equal to PA is equal to PI minus EX. EX will be what? PT minus PI minus PT minus PI. So plus PI, so 2 PI minus PT. Then this is the pressure of A at A. So how did you write the equation with respect to the, if it is a gas phase, you have to take the concentration in terms of partial pressure that you have studied in solutions itself, right? Gaseous solutions also. Okay, so what is this? K is equal to 2.303 by T into log of initial pressure by the final pressure. Final pressure is P. You know all these stuffs right now. So this is the formula. Okay, based on this, you are given this equation. So dinitrogen pentoxide is given. It is decomposed. It is a gas. It is decomposed into nitrogen peroxide, dinitrogen peroxide, and oxygen. Okay, go through this. Based on the given numbers, you have to perform the equation. Then half-life. It is very interesting. Suppose for a zero order reaction, the rate constant you have written is like this. Okay. What is T half? T half is you have to substitute in the place of T the half. That is T half. And the initial concentration is now the final concentration. Okay. When the time period is half, what will be the final concentration? It is also reduced to half of the initial concentration. Okay, that's what given here. Okay. So R naught minus half R naught. In the place of R, you have to substitute half R naught by T half. This is the condition. Okay. So T half is equal to R naught. R naught minus half will be what? R naught, you are substituting minus half R naught. So half R naught. So T half is equal to half R naught by K. You can just exchange this, swap this. So, okay. So this is for the T half-life period of a zero order reaction. It is directly proportional to the initial concentration. It's very great, right? And inversely proportional to the rate constant. You'll be asked like that. Keep in your mind. So this is the way you'll be asked in a one word. For a T half for a zero order reaction, how it is depending on the, initial concentration and rate constant. Okay. For a first order reaction, this is the equation. You need to put as T half and R as half R naught. If you substitute here half R naught, then these two gets cancelled. So log of 1 by 2 will be there. Okay. So log of 1 by 1 by 2, that will be log 2. Okay. Log 2 value is 0.3010. And you can substitute and find out. This is the T half of the first order reaction. Can you see anything? Now let me know, children, how did you know about the dependency? Okay. Can you say what is the dependency in this? Okay, it's very, you have to notice this is critical. Okay. For a first order reaction, half-life is completely independent of initial concentration. Right? Can you see any R not here? Okay. So whether you start with 10 mole or 100 mole, it takes the exact same time to reach half. Interesting, right? You'll be asked definitely the question from this half-life period. Okay, half-life period of a first order equation, since it doesn't depends upon the initial concentration. So for 10 mole of concentration or 100 mole of concentration, it takes the exact same time, okay, to reach half. Keep in your mind. So this is very important. So you must know the difference between zero order and first order, everything. And okay, so you know all these things. Okay, then we'll study about the pseudo first order reaction. So what is the pseudo first order reaction? Reactions that are second order, bimolecular, but follows first order kinetics because one reactant is present in large excess. Okay, that is what given here. First reaction, it is acid hydrolysis of ethyl acetate. Okay, so this is ethyl acetate. Like an ester it is. So it is hydrolyzed to bring acid, acetic acid plus alcohol also. Here, since H2O remains effectively constant here, the concentration of H2O is constant. Okay, We have taken this. And how we can write the rate now? Rate is, rate depends on rate, right? How we can write? K into concentration of CH2, COO, C2H5. Sorry, CH3H5. Okay. So, how we can take this is remains constant. So, hydrogenation takes place. H plus hydrogenation takes place. The concentration of water does not get altered. That is the meaning. It remains constant effectively, much during the course of the reaction. So the reaction behaves as first order reaction. Okay. Such reactions are called pseudo first order reaction. This is the main point you need to consider. Okay. The reactions that are second order bimolecular, okay, two molecule, but follow first order kinetics. Okay, because one reactant is present in large excess and it is stable, remains stable. Okay, another example also given, inversion of cane sugar is another pseudo first order reaction. C12H22O11, it is again plus H2O, it is hydrogenation takes place, right? Excess of hydrogen, water is there. Okay, then what will happen? It produces glucose and fructose. It is the pseudo first order reaction. You can take this. Okay, then this is very important point, temperature dependence of the rate of a reaction. Okay, so what is the temperature dependence? Here only you are going to study about the Arrhenius equation also. It's a famous equation. Okay. I will ask you students, why do we keep food in the refrigerator? Hmm? You have plenty of answers. Okay. So you need to answer related to this lesson. Okay. Cold temperatures. So in a refrigerator, only cold temperature is there. It slows down the biological chemical reactions. That is, the food is very slow to get rotten stage. That's what. So most chemical reactions roughly double or triple their rate for every 10-degree rise in temperature. Can you able to understand? So this is very, very important thing. Most chemical reactions, okay, it is double or triple their rate for every 10-degree rise in temperature. So if there is any, so that in summer and all, the food may rotten very easily. If you bring lunch box to your school, definitely you may experience. If your mom cook very early, okay, and then if it is more than 3 hours or more than 4 hours, the food may rotten very easily. Okay, so but in a refrigerator, since it is a cold temperature, there is no rise in temperature over there, so that the chemical reactions are slowed down. Okay, so this is the main reason. So Arrhenius, he was a scientist. He quantified this relation using the Arrhenius equation. So that Arrhenius equation is this one. K is equal to A into E power minus E suffix A by RT. This E suffix A is the activation energy that we are going to learn right now. A is the Arrhenius factor or the frequency factor, how fast it is, chemical reaction takes place. Okay. Then you can see Arrhenius frequency factor, that is the pre-exponential factor, we can say. Before exponential, it is there, right? So you'll be given pre-exponential factor also. Okay, it is constant specific to a per particular reaction. R is gas constant, universal gas constant. Its value, you will be given this value in your question paper, 8.314 joule per Kelvin per mole. So this is joule per Kelvin per mole. This is actually the gas constant, and T is here. T temperature is there, so it is absolute temperature in Kelvin, we can say. The total E power minus EA by RT, the total will be what I can say, Boltzmann factor. It is Boltzmann factor. The whole will be Boltzmann factor. Okay, so this is the fraction of molecule having energy which is greater than or equal to EA. That is the activation energy. Okay, if you take natural logarithm on both sides, then you will be getting this equation. You can get natural log on both sides because here it is E, right? We are reversing the equation. I'll teach you this. Okay, what is this here? Ln k. Can we write like this? Ln k. You are taking natural log is equal to ln. Here a is available, so we'll do like this. Okay, k by a is equal to e power minus ea by kt. Sorry, by rt. E suffix a, not e into a. E suffix a. To write like this. So ln of k minus ln of a, e gets cancelled, right? So it will give EA, negative EA by RT. Ln and E gets cancelled. You take ln here. Okay. Then if you want to convert into log, then how come you convert into log? You need to multiply by 2.303. So convert this into log now. 2.303 into log of k minus again 2.303 log of a is equal to 2 here no 2 point, okay, minus ea by rt. Okay, so whole divided by 2.303. So here also 2.303. That will give log of log to the base 10. Log means log to the base 10. I told you, right? Log of k minus log a. So k by a is equal to minus E suffix A by 2.303 into RT. Where R you know and T you know, that is the absolute temperature. Okay. So what is this activation energy? So that is what we are going to study about. Here in your book it is given hydrogen plus iodine. Okay, so hydrogen and iodine. What is hydrogen and iodine? See, hydrogen, it is the diatomic molecule. Iodine also diatomic molecule. It is bonded with single bond, like this. And it provides two high chain. Okay. See, according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. This is the unstable intermediate. So it bonds about to break like this dotted line it shows. Okay. And then it forms an unstable intermediate product so that it starts colliding together. Okay. Then so it exists for a very short time and then breaks up to form two molecules of hydrogen iodide. Okay. So the energy required to form this intermediate, that is called activated complex. Okay. And it is known as activation energy. Can you able to understand this? Okay. This is activation energy. That is, I can say students take notes. The minimum additional energy required by reactant molecules to form the unstable activated complex. That is the transition state. It is known as unstable activated complex that leads to products. Okay. Or we can say this one, if you plot like this, okay, what it says, okay, this diagram shows potential energy in the y-axis, reaction coordinate in the x-axis. So what are the reaction coordinate? Initially, it is hydrogen plus iodine. It forms intermediate activated complex. And then here only the activation energy, the potential energy is high. Okay, initially the potential energy is in this level and it is high, little high, so that the energy is needed for the electron, for the molecules to collide to form a intermediate compound, and then it slows down and goes until this. So this is this shows it is slows down, right? The potential energy is very much low. It shows that the reaction is complete. The product is formed. Can you able to understand this? It is nothing but it shows the activation energy of a hydrogen iodide. Okay, reaction coordinate represents the profile of energy change. Okay. So here the distribution of kinetic energy may be described by plotting the fraction of molecules n suffix E by n suffix R. Okay. See, all the molecules in the reacting species do not have the same kinetic energy. Kinetic energy means that is needed, right? That's what we are saying. We are seeing right now. Chemical kinetics. So the reaction molecules are moving. Due to the virtue of its motion, there is kinetic energy. And it is not having the same kinetic energy since it is difficult to predict the behavior of any one molecule with precision. So Boltzmann and James Clerk Maxwell, they use statistics, not any experiment, to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules n suffix E by n suffix R. With a given kinetic energy E versus kinetic energy. N suffix E means it is the number of molecules with the energy E. N suffix T is the total number of molecules. Okay, see, they are saying not all the molecules are suffering with kinetic energy. It is not necessary in a volume, in a taken volume, it is not necessary for all the molecules to move, okay, to take part in the reaction. Okay, that's what they are trying to say. So a part which is having energy is n suffix E and the total number of molecule is n suffix T. So this is the ratio and the kinetic energy, distribution of kinetic energy is distributed. This is the fraction of molecules. The kinetic energy is distributed like this. It shows the distribution probability, okay, with the given kinetic energy versus kinetic energy. This is the most probable kinetic energy, maximum kinetic energy. So the peak of the curve it describes, okay. There are decreasing number of molecules with energy is higher or lower than this value also. You can able to see the distribution, overall distribution that shows, okay. Then, if the temperature is raised, we saw actually every 10-degree rise of temperature, the reaction actually it increases, right? That's what activation energy we saw. See, the chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled or tripled like that. So we can say here, if temperature is raised, then what will happen? Okay, so it is happening here. If the temperature is raised, then the chemical reaction takes place. The maximum of the curve moves to the higher energy value, right? The maximum of the curve, it is moving to the higher energy value. The figure 4.9 it shows. And the curve broadens out, right? And the curve also broaden. Highly it is broaden. And it says it spreads to the right such that there is a greater proportion of molecules with much higher energies. That's what from this to this much proportion of molecules have higher energies. Here very small, right? Like that. If the temperature increases, then the kinetic energy increases. That's what they are saying. Okay, spreads to the right such that there is a greater proportion of molecules. See, they are looking, the kinetic energy increases, right? In that aspect, their perception is something different. Their perception is like the distribution of molecules. They are talking about the kinetic energy increases means the distribution of molecules also increases in terms of this fraction of molecules. Fraction of molecules, the number of molecules which attains energy, kinetic energy, divided by the total number of molecules. So now the number of molecules are increasing. That's what with the energy is increasing when compared to the total number of molecules. That's what for every 10-degree rise of temperature. Okay, this is very interesting. These two guys are very, very talented. Huh? I mean, this Boltzmann and James Clerk Maxwell, these two guys are very talented. Boltzmann was, he did, I mean, he was a mathematician. He did a lot of mathematical analysis in chemistry as well as in physics also, especially in thermal physics and thermal chemistry. Okay. And this particular Maxwell Clark also, James Clerk Maxwell also, he did much in his inventions, and he did statistical studies. So using all those things, statistical means all probability. Statistical means it is probability. So this distribution is normal distribution, we can say. There are a lot of distributions you will be learning from the probability. It's purely mathematical. Normal, Poisson. There are a lot of probability. Okay, so standard deviation and normal distribution, Poisson distribution. So he used all these mathematical statistics to derive, okay, how the distribution of molecules takes place. That is, the kinetic energy increases for every 10-degree rise of temperature. That's what he was saying, the activation energy. Okay, so the energy, the number of molecules carrying the energy. So that is what the fraction is divided by the total number of molecules. Okay, then if there is any catalyst in that, so a catalyst, if you add any catalyst, then what will happen? Catalyst lowers the activation energy by providing an alternate pathway. I told you already. Okay, it increases both forward and backward reaction rates equally, leaving the equilibrium constant and delta G unchanged. That won't be changing. But the activation energy is lowered and the pathway is altered. That's it. So I can say the activation energy is equal to threshold energy. Threshold means it is the value, critical value. At what particular temperature, or at what particular value it started becoming the product. So that is the threshold energy. Minus